Okay, so welcome everyone to the last session of our algebra seminar. Today we are glad to have Professor Eduardo Marcos from Universidade de Sao Paulo. He's going to talk about the Braid group action on exceptional sequences for weighted projective lines. We have also new audience today, so welcome to our seminar. And okay, Eduardo, so if you're ready, go ahead.
Ok, gracias por la invitación. Eu vou falar só agora segundito em espanhol, depois em portunhol. E depois câmbio para inglês, porque aí dos colaboradores que está mirando, que está aí, é uma pessoa, alemão que... Bueno. Then, this is the title, the Braid Group Action on Exceptional Sequence for Weighted Projective Lines. Thus has a flavor, the paper is, there's 3 authors there, and the paper has a flavor of geometry and a flavor of representation because it's the subject. I like to say that the authors received, the 3 of us received the financial help from FAPESP. I have a project with FAPESP that go for over the year, and I also have some financial help from CNPq, and I also like to say that the beginning of this project happens when Hagen, I invited Hagen to come to Brazil, and also we went to a conference in Rio de Janeiro. That was a conference of the Franco-Brazilian Sociedade Franco-Brasileira de Matemática, projeto que havia, e recebemos lá a estadia aí gratuita, então queria agradecer a eles também. Bueno, this talk always denotes an algebraically closed field, fixed and once and so on. And the talk is divided as follows. The main result, we give an intrinsic proof of the transitivity of the Braid group on a set of full exceptional sequence of coherent sheaves on a weighted projective line. It's interesting to say that we don't use at all the corresponding result from Crawley-Boevey for models over hereditary algebras. Crawley-Boevey also showed that there is a Braid group action, and was our inspiration, one of our inspiration, but we don't, our result is completely intrinsic. Ok, e agora ele não quer fazer mais. Ai, saco, por que aconteceu isso? Bom, eu não sei o que acontece aqui. Bom, we have some applications. An application, we prove that the strongest global dimension, a notion that is going to be defined, clear, of the category of coherent sheaves on a weighted projective line does not depend on the parameters of X. Every word of the statement is going to be explained during the talk. Application 2, finally, we proved the determinant of the matrix obtaining by taking the values of any linear function defined in the Grothendieck group of the elements of a full exceptional sequence is an invariant up to sign. Okay. Não sei por que I don't understand. Definition, then that's the definition. A weighted projective line. Now, a weighted second, I'm going to define a weighted projective line. A weight sequence is a sequence of t natural numbers, p1, p2, pt, which each number is bigger or equal than 2. Okay. For a weighted sequence P, we denote the LP is the abelian group generated by T elements that I denote by x1, x2, xt with an arrow above, and the relations that there are P1, x1, pt, xt equals C. It's completely clear that those abelian groups has rank 1. And a sequence of parameters is a sequence lambda equals of t minus 2 numbers, where lambda I and lambda and pairwise distinct elements of Q. In reality, we are taking points in the usual projective line, and P1 we take to be 1, and P2 with lambda 1 that doesn't appear here is always fixed 1, and lambda 2 is the infinite also. Okay, so we are that's how we if you want to consider very geometrical. Okay, given all the setting, we define a commutative group a commutative ring that is this commutative ring of any unknowns, divided by this x1 to xi to the p1, xi to the pi, and then x1 to the p1, lambda I to x2 to the p2, and I goes from 3 to n. So we have here t minus 2 relations, and so we have this ring that has crew dimension 1, and the algebra graded crew dimension 1. The algebra SP lambda is a graded algebra. We grade this ring here. We grade in the LP grading. We grade by LP, simply declaring that degree of xi is the small xi with an arrow above. If you look at this, it's clear that all the relations are homogeneous by the way we define. Okay, so it's really this ring is a graded ring. So the way to the projective line is defined is the LP projective scheme. That is the projective scheme defined by this ring. So it is okay, and the category of coherent sheaves on X is by a theorem of Serre, is the quotient of the category of finite length LP graded S modulo by the LP graded modulo of finite length. So you consider the category of LP graded modulo, and you declare that all modules of all LP graded modules of finite lengths are 0, and so you divide by the category, and this is equivalent to the category of sheaves. I think there is no way. Okay. Is interesting to note that this category is an hereditary category. What I mean by that, I mean that x2 in this category is an abelian category. You can talk about x's. The x2 blank is always 0. So all the x2 vanishes. Only x Holmes and x1 appear. So I want to tell you one thing, that if you have an abelian category that is hereditary, that Holmes between objects are finite dimension. It's a K category. Holmes are finite dimension. X1s are finite dimension, and it has a tilting object, then the category is either a category of sheaves over a way to the projective line, or a category of modulus over an algebra KQ, where Q is a quiver without oriented cycle. There is only those two categories that are hereditary with all those properties that I said, that has finite, the homomorphisms are finite and have finite length. For does algebras of categories that are of the type KQ are called quiver type, and that are of the type of this type that are telling here, coherent sheaves are called sheaf type. They have a big intersection. They have an intersection that are the same algebras, hereditary algebras. They are both. They can be considered in both ways. So quiver time and sheaf times are not complementary. I mean, they are one. There are things there are categories that are sheaf times and coherent sheaves. They are both things. How are they in the composables in the category of sheaves? In the category of sheaves, we can divide the incomposable first of all in the sheaf category two distinct things. One is that are the sheaves of finite length, and in the composables they all have support in one point only, and they are in the composables. And there are what we the non-finite length. The non-finite length we also can divide in two parts. There are the ones that have rank 1 and the ones that have rank bigger than 1. Okay. Now a definition of exceptional sequence, that is where the braid group is going to act. An object in a hereditary K category H is called exceptional if his endomorphism is K and x to 1 E is 0. We are assuming that K is algebraically closed, then that's why we put the endomorphism of E equals K. Moreover, a sequence of objects is called an exceptional sequence if a sequence of exceptional objects. They are called exceptional sequence if the home coming from bigger index to a smaller index is 0, and the x to 1 is also 0. We already have that the x to 1 EIE, but so does is an exceptional. Does it can define an exceptional sequence in any abelian category in some sense, but usually to define an exceptional sequence, you are going to require is if the category is not hereditary, that all the xi's that appear here as x to 1 have to be 0. Okay. If R equals 2, or if there are 2 elements, then epsilon is called an exceptional pair. This is a case. And if R is equals the rank of the Grothendieck group, K0 of H, the category is H, then epsilon is called a full exceptional sequence. This name is reasonable because you can prove that every sequence, every exceptional sequence has at most R entries, at most R entry, and every exceptional sequence with you have less than R can be extended to an exceptional sequence. So it's reasonable to say what you're saying. This was an inspiration for all the work that Grothendieck and Rudakov, they define mutation of exceptional sequence on vector bundles of Pn, which gave rise to an operation of the Braid group. Just to recall here, the Braid group is the Braid group BR is generated by R minus 1 element with this property there. So is an order, and every time that the index if where is I minus j is bigger or equal than 2? Yes, okay. They commute if the index, the difference in the index, the modulus of the difference is bigger or equal than 2, and have this O relation on the set of one important quotient of the Braid group is the symmetric group that is obtained by declaring that sigma I to the square equals 1. Okay, they are group generated by the 2-3 transposition, what the notion. We analyze the action of the Braid group where n is the rank of K0 of x in the set of a exceptional sequence. And once more, I want to say that the definition was inspired by Grothendieck and Rudakov. Okay, that's what I'm going to do. I will prove this theorem and then state two consequences. The consequences I will not prove, but I will state. I start with a lemma that could be an exercise, but I will prove. To start with something kind of easy and nice. Let A an abelian category an n object whose endomorphism ring is a finite dimension K algebra. We only need really that the does is a finite length is a finite length ring is the endomorphism, but let's assume that it's a finite dimension K algebra and left F an element in the endomorphism of n. Then the following are equivalent. F is a monomorphism, F is an epimorphism, F is an isomorphism. Okay, I will prove that 1 implies 3. I will prove that 1 implies, I will prove that clear 3 implies 2 and 1. 1 implies 3 and 2 implies 3 is more or less the same proof. Let F be a monomorphism. We can assume that F is not 0, obviously. Otherwise, there is n such that this guy is linear dependent because the endomorphism ring is finite dimension. So there is a non-trivial linear combination of this to be 0 with lambda t and lambda n non-zero. So we factor ft and we have this. Since ft is a monomorphism, this guy here is 0, which implies, putting the other side, lambda t equals the sum here. Now we can factor f, and f is invertible. Okay, and that's the proof. Very nice and easy, simple, but nice, but important. Corollary, let us assume the same hypothesis as in the lemma. If m and n are objects in A, and there are monomorphisms f from m to n and g from n to m, then f and g are isomorphism. Okay, I'm assuming here that the endomorphism of m and the endomorphism of n is finite length. Analogous thing is proved is valid for epimorphisms. Now I have to explain to you how is the Braid action. We need the following lemma. In order to explain how the Braid action group, we need the following lemma. This action is similar to the one, once more I want to say that is similar to the, we didn't create the powder gum here. It was really inspired by the action of Grothendieck and Rudakov on the vector bundles of Pn. Let A and B be exceptional sequence. Then the trace map, this K is, the tensor product is over K. So it's just copies of the exceptional sequence A with the dimension thus. And there is a canonical map that we call the trace map that is F tensor A goes to F of A. And I claim that we showed that this is either a monomorphism or an epimorphism. The proof is very similar to the one of Hagel given for modulus, and I think I will not do the proof here because I don't want to spend all the time thus, but I will go very quickly to thus. So what we want to show is that thus is mono or epi. And no, I think I will keep, if I have some time, I will go to another proof, I will show this proof. So, one thing that I didn't say is that if you have an exceptional pair, either x1 of a, b is 0, x1 of a, b is 0, or home of a, b equals 0. Then they cannot be both non-zero. So, and the left mutation is defined in the following way. There are four cases. The first case is if the home and the x is 0, then the mutation of the pair is just taking b, is a transposition, it's called a transposition. You transpose b and a. This is the left mutation. There is a dual notion, the right mutation. Here is going to be the same. Okay. In the other cases, the LAB is using the 3 exact sequence. Okay. If the home AB equal different from 0, then X is 0. Like I said, this map here can be epi or can be mono. If it's epi, then the kernel here is the left mutation. If it is mono, the co-kernel is the right mutation. Okay, this cannot be ISO for very simple reason. So if this is epi, LAB is different from 0. If this is mono, LAB is also different from 0. So this is the case where x1 AB is different, where home AB is different from 0. Now assume that home AB equals 0 and x1 is different from 0. Okay. If x1 is different from 0, so home is 0, then this is the dimension of x1. So there is one thing that is called the universal extension. You take here copies of A, exactly the one that you exactly how many copies as the dimension of x1. You can take a basis of the space and define the universal extension. And the universal extension is unique, is very well defined. And then in this case, the LAB is the middle term of the universal extension of this object here. Okay. The generator sigma I on Bn act on the set of full exceptional sequence by taking the sigma I acts taking doing the mutation between EI and EI please one here. We have to show that does obeys all the properties of the Braid group, and this can be shown. So it is now I'm gonna give some ingredients of the proof that the action is transitive. First, we have that if we do sigma n, sigma 1 of En, we shift in the sequence everything to the right, and En gets on the beginning shifted by omega. Omega is a very special element on that group that I had in the right beginning. And here also we have this orbit, and so we have as a consequence of 1 and 2 that in the orbit of an exceptional sequence, if you take an A bigger than 1, there is an exceptional sequence it starts on A1, AN, goes to EN plus 1, and then some shifts of the other ones. So we can, doing a shift is assumed, doing an action of the Braid group, you assume that we start in AA. And the W is this element here. Okay? It's T minus 2 C plus this guy here. This is the dualizing element. It gives a seg duality tensor it with the canonical shifting OW gives you, or shifting by W, gives you the one thing that's called a seg duality, because it has some properties that it has to do. Okay, proposition. Let L and L prime be an exceptional pair of line bundles. Line bundles are the indecomposables that have rank 1. That are the line bundles. That are the line, it's a particular case of vector bundles, but when we say vector bundle, we usually think that is not a line bundle, but only suppose the dimension of home L prime is bigger or equal than 2. Then L prime is isomorphic to L shift by C, and the dimension is 2. Okay, so does usually if this home is different from 0, except in this particular case, this dimension is going to be 1. The left perpendicular category with respect to LLC for a line bundle L formed in coherent of shift in the category of consists only of finite length shift. So all modules that are left perpendicular to this, left perpendicular means that the home and the X are 0. They are shifts of finite length. Okay. Let's prove A. So in A we have L prime 2 line bundles, and we assume that this dimension is bigger or equal than 2, and I want to show that then L prime is given by this case here, and this is 2. This is, and also the second thing, this is, I improve A or B, and B does uses various ingredients, and it's a nice proof, not so easy, but nice. First, let's prove the first thing. Okay, without loss of generality, assuming doing some things, we can assume that L equals O and L prime is O of X. So all the line bundles are of define O of X, and you can shift and assume that L is O and L prime is O of X. And X can be written this way for some R. Let me explain a little bit what happens. What happens is that one can prove in the group that I define, in the group that grade, one can group that every element can be written in a unique form, or as X equals LC plus some here, where this Li has to be between 0 and P minus 1. One can show, and then the form is unique. If we go X to the P, we can put an L here. So we assume that X is written in the normal form. This guy is different from 0. I'm assuming we can for some R. Okay, the ones that are 0 we don't write, so we can assume this. Okay, using Serre duality and the fact that this is an exceptional sequence, an exceptional pair, we have that 0 is X to 1 of OXO is isomorphic. That is the second duality. That's the importance of this W here. The second duality says exactly this, that X to 1 of OXO is isomorphic to home OXW. let me tell that to have a select duality is equivalent to say that the category of sheaves have almost split sequence. This is equivalent. The select duality is equivalent to this. Okay, now x plus w is written, which x was this, and then I put w, I add w, and then I do some computation, and this element here now is in the normal form. Is in the normal form because this guys are in this is positive, and does the home L with OX is always home O with something, is always this L here. The dimension of the home is always L plus 1. Exactly. Okay. Now, okay. The fact that this is the normal form, it follows that this guy is bigger, is smaller than 0, and it follows that L equals 1 and R equals 2. And because L equals 1, it follows also that the dimension of the homomorphism is 2. When you write in a normal form, so the dimension of A is 2. Consequent, X has to be C. So that's what happens. The second statement, let's look at the second statement. The second statement says that the left perpendicular category to L plus LC for a line bundle is formed in coherent sheaf consists only of finite length modules, finite length sheaves. Let's see how is the proof. This proof is more complicated than the last one and uses some other ingredients. Okay. Without a lot of generality, we can assume that there are one tube that the category of sheaves, if you think in the Auslander right and quiver, it has one set of tubes for one for each eye in the x eyes, and then there are other kind of components. But then we can assume that x to 1 SIEL equals 0. This is not difficult to assume. Not a very, you can re-indexing. We know that x to 1 of SIT L is different from 0, and you can take this T, do a shifting on L and etc., and suppose that this is 0. Then we have a formula that is exactly the same formula, exactly the same, is the analogous of the Riemann-Roch theorem. And this formula says that this tau here is the Auslander-Riemann translation, and this formula, this Riemann-Roch formula say that if you have this guy here, this is Holmes minus X, so you have this quadratic form here, and this is given by P1 minus G, the rank of SE0, rank of L, and the determinant of this guy here. In this formula, P is the minimal common multiple of all the PIs, and G is the genus of the weighted projective line. There is a notion of genus, and this is the ring. This is the formula. Using this thing and the Euler form that is already was used here, the Euler form, that's the dimension of the home minus dimension of the X, we conclude that, therefore, that the finite length sheaves, belong to this there are those guys belong to the left perpendicular category. H equals L plus left perpendicular category. We can conclude that the category H is the category of modules over an hereditary algebra whose quiver, this category H is this thing. We take this. We can prove that is the category of modules of an hereditary algebra whose quiver has n minus 2 vertices. Okay, consider the following object. It does consist, here appear n minus 2 in the composable direct summands and x to 1 tt equals 0. So there is a tilting sheaf in H, and consequently, H consists of objects on a thing called a wing, and thus shows that the endomorphism also of T is the disjoint linear of is the union of disjoint linear quivers of type AP minus 1. I went a little bit fast, details can be found in, but the general idea is there. Okay. Now we use three following results of Hagen-Meltzer that I just state. I don't give the proof here. Two distinct complex, complete exceptional sequence differs in at least two places. There is for the category of Q mod, does lemma already appear in the category of modules by Crawley-Boevey. It shows this, but it takes exceptional sequencing in Q mod. So if you have two distinct exceptional sequence, they have to differ in at least two guys. They cannot be. So if you have n minus 1, it can be completed just in one way in each position. One can show this. There are no complete exceptional sequence where home EI EJ equals 0 for all pi pairs AJ. So if you have an exceptional sequence, then some home has to be different from 0. They cannot be home orthogonal between them. They cannot be. And another lemma, let E1, En be an exceptional sequence such that the dimension of E1 is 2 is bigger or equal than 2. Suppose that LE2 is defined by this exact sequence. There are two ways to define. Suppose that then, suppose the canonical map. I'm assuming that this is different from 0. Suppose the canonical map is an epimorphism. Then every morphism from E2 to E1 and from E1 to E2, from the L of E1 in E2 and L of E1 and T, they are both monomorphism and epimorphism, or both epimorphism. I mean, all morphisms are mono in both of them, or all morphisms are epi in both of them. And the same thing happens if the canonical map is a monomorphism. We have this kind of the same thing. Okay, then you have a lemma. Suppose that there's an exceptional sequence and the dimension is bigger or equal than 2. Well, that's what I said here. And also we have this thing, the same if this guy is an epimorphism, if there is the other sequence. Then we can prove using these facts that if X is different from P1, then in each orbit under the Braid group action, there is a complete exceptional sequence containing a simple module. One can show this using, so in every orbit we have a simple modulo, and using the fact that every module in every think you have a simple modulo. We first showed that in every orbit there is an indecomposable finite length. You do, and then taking one of those finite, we can conclude then the action is using this, and some more thing we can conclude that the action is transitive. Okay, so that is the general idea of the proof. I know that is not completely clear. Some things are a little bit obscure, but the flavor of our proofs, I think I transmitted. Okay, the strongest global dimension. We first recall that the strong global dimension of an algebra, you gave an algebra, what is the strongest global dimension? It is the maximal length of an indecomposable object in the homotopy category of complexes of projective model. That is always smaller or equal than the bigger or equal than the global dimension. Bigger or equal than the global dimension. Okay, so algebras of infinite global dimension have infinite strong global dimension. Recall that the strong, okay, we gave the following definition. Okay, the strong global dimension, the strongest global dimension, this definition is ours, is the maximum of the strong global dimension of all the strong global dimension of coherent sheaves of X. Is the maximum of the strong global dimension of all algebras which are derived equivalent to coherent sheaves of X. And this is denoted by this. This is the strongest global dimension. Okay, one thing, there is a proposition that describes what is the stronger global dimension. This is a characterization that appeared in a paper, it was very used in a paper by myself, Alvarez, and the French guy, but I'm getting old. Okay. Patrick Lemaire. Okay. We use this thing that this is a characterization of the strongest global dimension of X that depends on how the spreading of the tilting in the derived category. Okay. The first consequence that we have of our theorem, of our action and also of the proofs, is that suppose you have two weighted projective lines with the same weight, but the parameters, those are the parameters, are different. Then we can show that the strongest global dimension of X is equal to the strongest global dimension of X primes. That is, the strongest global dimension does not depend on the parameters. So you can choose the parameter the way you want. For instance, you can choose everything to be 2, 2, 2. You can choose anything you want. The strongest global dimension is not going to change. So you can, and we have a conjecture. The former proof also suggests the following conjecture. Let T be a tilting complex of this form with T incoherent sheaves and Ti, Tn equal to 0. Suppose that A is ended in T. The strongest global dimension does not depend on the parameter. We have, I have to explain of this because I'm taking tilting complex in different places. But using our action, you can show that if you have the same projective line, two projective lines with the same weighted, you can do a bijection of the tilting objects, the tilting complexes, in one of the lines with the tilting objects in the other line. So what we are taking here is this bijection that you have. So we have that. One thing is that if we could prove that does not depend on the parameters, we would have another proof of the former of the problem of the strongest. I really believe that this proof, this conjecture is true. I already thought three times that I had a proof, and this would be a nicer, another proof of the former conjecture. Now I'm going to talk about the determinants for exceptional sequence. Let F1F group be a group of homomorphisms, defined on the Grothendieck group with values in Z. For a full exceptional sequence, we can form the n by n matrix, where in the place A, Ig, we have Fi of Ej, and we consider this determinant here. And what we can show is that there is a constant C in K, such the determinant of this guy is C or minus C. Does not depend on the homomorphism. So it's in particular, we can apply this method above to the rank function, the degree function. There is a degree function. And the n minus 2 Euler form. Thus, we fix with Sij, where for j goes from 1 to pi minus 1, and I goes from 1 to 2. And then we have that for each full exceptional sequence, for each exceptional sequence, independent of what is the exceptional sequence, we have that this matrix here. That is just applying our theorem. We can show that this is P or minus P, where P another time denotes the least common multiple of P1, Pn. This can be understood as solution of some Diophantine equations that was Rudakov also showed in his case. So this can be understood as solution of some Diophantine equations that I don't put here because my time is almost over. Muchas gracias, muito obrigado, thank you very much, health to everybody.
Thank you very much, Eduardo, for your nice talk. So now we have some minutes for questions from the audience. So if anyone wants to ask something or a comment, please feel free to participate. Questions can be in Spanish, Portuguese, or English. No questions? But I have one, Eduardo. In your results, is it reasonable to change the hypothesis of coherence for quasi-coherence? I mean, if you consider, for instance, the bigger category of quasi-coherent sheaves over X, could you get a generalization of those results, or? I never knew
any paper where the people studied the quasi-coherent sheaves over weighted projective. I really don't know. If some of my co-authors wants to say something, Hagen, if you want to say something, I really don't know. I really have no idea. The category of coherent sheaves is very studied over the weighted projective lines. In particular, Hagen has some of the results. He has a nice book on the subject, really very well written with care, and sometimes it's not easy, but it's always very well written. But he studied study also the weighted projective lines in general on various things, and but the category that appear there is the category of coherent sheaves, of the quasi-coherents. I don't know.
Okay, cool, thank you. Perhaps it has something to do with the working with finite dimensional algebras. So not sure.
Yes, and then if we go quasi-coherent, it's going to be harder to find
right.
To find it, because does derive the category, the sequence here, because it has a tilting module, is always equivalent to a category of a finite dimensional algebra. There is even one finite dimensional algebras, class of finite dimensional algebras called canonical algebras, and they are defined using the parameters and etc. And the canonical algebras are derived equivalent to the derived category of coherent sheaves. So the category of coherent sheaves is, in this case, is equivalent to the derived category, is the equivalent to the derived category of triangular equivalent to the derived category of a finite dimensional algebra.
I see.
Can I add something?
Yes.
Sure.
So concerning the question whether it is reasonable to go to the quasi-coherent sheaves, so first of all, you also have the action of the Braid group. In fact, you have the action of the product, semi-direct product of the Braid group and the group and copies of the integers. And this action works. But it is not studied. We have not studied the question whether this action is transitive. It is, of course, a reasonable question, and I guess that the answer is yes. But we have not studied this, and also the Russians, which have studied the action of the Braid group on vector bundles, on PN, or more generally on Del Pezzo surfaces, they always they always studied the action only in the case of the smaller category of coherent sheaves. So I have not seen any result about the quasi-coherent sheaves. But if you ask me, so I would rather think that the action is always, it is also transitive in this situation.
Oh, cool. Thank you.
Thank you. I knew that he would say something. Okay.
So any other questions? Well, it seems there are no more questions.
I have one thing to say. In the beginning, you said that this is the last seminar. I hope not. I hope this is the last seminar of the semester.
Yeah, sorry for that.
No, I'm kidding. I'm joking.
I meant it, the last session.
Obviously, you meant that.
Actually, we're retaking the seminar in mid-August. So if anyone is interested in giving a talk, so feel free to write me. I'm gonna leave my email address in the chat. So there. So, well, no more comments or questions so far. Well, again, thank you everyone for coming. Thanks, Eduardo, for your nice talk. Well, we'll meet again in mid-August.
Okay, see you in August.
See you.
Okay.
Not presentially already, or not presentially, because it's the pandemic. Will be there in August, I think, at least in South America.
We'll continue through soon.
Okay. Bye-bye.
Goodbye. Thank you.
Goodbye.
Bye.
Goodbye, everyone.
Get out. Eu não sei como sair.
Si quieres, cierro la reunión simplemente. Aquí ya la voy a
Não
cerrar.
sei como fazer, porque ela está diminuída.
No, no hay problema, yo cierro la reunión.
Isso, tu segue a reunião ali, sale com certeza.